So right, we are going to study public key cryptography today. So up till now, what we have seen is the stream ciphers, block ciphers, but that all we have seen in symmetric key cryptography. What happens is in symmetric key cryptography, let's say there is sender and there is a receiver, and let's say the message X wants to be sent by the sender. Okay, so what you do is you use some encryption and then you send it over the internet, the encrypted message. Okay, and that is why. So what you do is you use some key. Okay, so ciphertext is produced using the encryption on input X using some key, right? And then the receiver, when it receives the message, you do the decryption part. Okay, use the same key to produce the original message X. Okay, so how do you produce the original message X? You have to use the decryption algorithm on ciphertext, whatever the ciphertext is getting transferred through the internet. So you use the decryption on that ciphertext using some same key. Okay, now here is the symmetric key encryption, right? In the other part, that is asymmetric key encryption, what happens is, let's say this is Alice and this is Bob. Okay, both of them will have their own public key and private key. Okay, but let us say A wants to send the data, the same process. Alice wants to send the data to Bob. Okay, so in this case, we will use the public key of Bob. Okay, let us name them key public and KPR, that is key private. Okay, this set of keys for Bob will be used in this case. Now, how will it be used? If Alice wants to send the data to Bob, he will get the public key of Bob. Okay, now either Alice can send the message to Bob, send me your public key, or it is already available in the internet. As it is a public key, everyone can have it. You can actually Bob can create a website or web page and publish this public key on that web page. Okay, so it is not at all secret. So Alice has the public key of Bob. What Alice does, it has X. What it will do, it will produce the ciphertext. And how will be the encryption done? There is some encryption algorithm will happen, but the key which is used is the public key of Bob. Okay, so the encryption will happen. Now this Y will be sent over back to Bob. Okay, now when Y is reached at Bob, only Bob can decrypt that data with this private key. Okay, so how Bob will do it? It will produce X. It will have the decryption algorithm. okay, on the ciphertext, but it will use KPR, that is private key. It will not use the public key. The same key will not be used. Okay. So this is how the original message will be decrypted by Bob. Okay. Now in this whole process, even if the attacker gets hold of whatever you are transmitting, get hold of public key or get hold of the ciphertext, okay, that attacker, let's say it is Darthi or Charlie or some guy, so it will not be able to use any of these to produce the original message because it doesn't have the private key of Bob. Okay. Now in this symmetric key, the problem is with the same key is used. When you are using this key for the encryption, Bob should also have the same key. Okay. Now in this symmetric key encryption, you should have some secure channel through which you can share the key itself, not through the internet, but through some other channel. And you have to make sure that this channel is so secure that some Darthi guy cannot access this channel or cannot have the hold of this key. Otherwise, there is no point in doing encryption decryption. Right. So this is the problem. Now, in this asymmetric key, what's happening is Bob is not sharing this KPR with anyone in the world. Okay. It will not be shared with anyone. It is not accessed. It will not have access to anyone. So only Bob can decrypt this particular ciphertext, no one else. And that's why this public key is very secure. Public key cryptography. This is called as public key cryptography. Or you also can call it as asymmetric key cryptography. Okay, so have you got the concept here? Any doubts? Now, when you talk about the symmetric key encryption, we have seen DES, AES, triple DES. There was a double DES also. And there are hundreds of such algorithms. Okay. When you talk about the symmetric key encryption. But for asymmetric key encryption, there are very few. There are only 3 algorithms. One is called as RSA. The other one is discrete logarithmic. Discrete logarithmic algorithm. And the third one is ECC, that is elliptical curve cryptography. Okay. So there are only these 3 public key cryptography or asymmetric key cryptography algorithms available in the world. Okay. And most of the communications are using the public key cryptography. This is the symmetric key cryptography is also secure only when you are very sure that the secure channel through which the key is getting exchanged is so secure, 100% secure. Then only the this has 100% effect. Okay. If you talk about the market share or the usage of public key, RSA has almost around 75 to 80% of market share. Okay, so everyone uses RSA, and rest of the usage is divided into these two algorithms. We'll see RSA and discrete logarithm probably. So let us try to first look at what is RSA. Okay, the algorithm which is used for the encryption and decryption. Okay, so if you have understood this concept, we can move ahead to check out what is RSA. Okay, so RSA was developed in 1977 or 79, I guess. I'm not very sure. It was designed by three scientists, Ravist, Shamir, and Adelman. Okay, so that's why the name is given as RSA. It's a very simple algorithm. If you think of DES or any symmetric key cryptography algorithm, the steps are so difficult, and it is very difficult to implement also. Okay, but RSA, what happens is the steps are so simple. Okay, there are only 5 steps. Okay, and most of the steps are on assumption. Okay, there are not much calculation is needed. Okay, as I have told you, these algorithms uses number theory, prime numbers, and all these things. So what you have to do is you have to take 2 numbers which are prime. Okay, they should be so large or large enough to have larger security. Now the size of the bit size 1024 or 2048 bits. We are talking about bits here. If you want to talk about digits, then either 300 digits or 600 digits. Okay, so such large numbers you have to assume. Okay, then second step is calculate the product. Very simple step. 2 steps are over. Okay, the third step is calculate phi of n. Now yesterday we have seen phi of n. What is phi of n or phi of n function? Anyone? I have to pull out. So what we have seen for Euler's phi function, for a given set or for a given number, you have to create a set for n minus 1 numbers, and you have to find out the number of co-prime numbers. That is phi of n. Okay, so here you have to calculate phi of n, and as you know that these are the prime numbers, the phi of n is very simple. For p minus 1, for phi of p is p minus 1, and phi of q is q minus 1. Any doubt here? Or what you can do is you can write a previous step of this. phi of n equal to phi of p into phi of q. For prime numbers, yesterday we have seen that, in the last lecture we have seen that phi of n is p minus 1 and phi of q is q minus 1. Okay, so this is again another simple step. Fourth step is choose the private key. I'm sorry, choose the public key. So let us assume that public key is E. Okay, such that, okay, now there is a condition. There is a condition. What is that condition? Is GCD of phi of n with E. GCD of phi of n and E has to be 1. Okay, and E should be less than phi of n. So there are two conditions. One is GCD of phi of n and E has to be 1, and E should lie between 1 to phi of n. Okay, so you have to choose any such number which have which satisfies this condition. Okay, now as you know that if you are talking about, let's say, let us consider yesterday's last example that we have seen. So let's say n is 7. You have 6 such sets which has GCD and that particular number, okay, has is 1, for which GCD is 1, right? So now you have to choose any set from these numbers. Okay, so that can be, if you think that this is E is equal to 3, so this condition is satisfied. GCD of E and phi of n is 1. Okay, and 3 is greater than 1 and less than 7. So if you choose any such number, that will satisfy these two conditions. Okay, and this is just number 7. It's a 1-digit number. If you have 300-digit number or 600-digit number, you think of how many such combinations are available here. Okay, and you have to choose one combination out of it. Okay, now the last step in the algorithm, that is the fifth step. You have chosen the public key. Now you have to calculate the private key. Let us say D is private key. Now how do you calculate D? It should satisfy such that D and E, D into E has to be equivalent, or what do you call this as, if you remember? Anyone? This operator is a congruent operator. This number is congruent to 1 mod phi of n. Okay, so this is how you have to find out D. Okay, or if you check out the book, it will also give you that D is equal to E inverse, okay, mod phi of n. This is also available in the book. Okay, both of these. if you refer any book, any cryptography. Okay. So now this is the complete algorithm. Okay. So we'll try to see one example while considering P and Q. Okay. And we'll calculate all these steps. Okay. So let us assume that and about the encryption and decryption, I'll just let me just give you that idea also. Okay, for the encryption and decryption, if you have a message M, okay, what you have to do is you have to use the public key, right? This is the original message M, okay. You have to raise the original message with the public key, okay, and you have to do a mod operation on N. Okay, that will produce a ciphertext. Okay, now while doing the encryption, you are using the public key. Key is a public key here, right? Now for decryption, what you have to do is whatever the ciphertext is there, okay, that raised to the private key. Okay, and again you have to do a mod operation on N, and that will produce the original message. Okay, so this is how the RSA works. Okay, now we will see the example, okay, of how when we consider the values, how that can give you the original this thing message and ciphertext. Okay, if you have any doubts, please let me know. I'm just putting this aside. Okay, so can we consider, okay, both of, I will give you the numbers here. P equal to 17 and Q equal to 11. Can you solve this on your paper? Few steps are very simple. P into Q will be 187. 17 into 11. What will be this phi of n?
Six zero.
Sorry,
160.
160. Okay. 60. Now here, fourth step, let us choose it 7. Okay, I'm giving you the number 7. You can consider any number for that matter, because for the set which is having 1, 2, 3, and so on till 1, this is a phi of n. Okay, 159. This is the set. Okay, GCD of 1 and 160 is equal to 1. 1 and I'm sorry, 2 and 160 is equal to 1. 3 and 160 is equal to 1. Okay, and so on. You can consider any number as a public key. Okay, because what uh, fourth step tells you, you have to choose E such that GCD of phi of n, this is phi of n, and E, whatever number you choose from this set, has to be 1. Okay, and all the this thing, all the numbers in this with the 160 will be 1. No, it's not all the numbers. 160 is not the prime. Okay, the prime is this one, P and Q, but not the phi of n. Right. So let us find out GCD of 7 and 160. What is 7 and 160 GCD? Is it 7?
So it's 1.
It is 1. So it is satisfying this condition and it also satisfies this condition. Okay. Now can you calculate D such that when you multiply uh, E with D, it should be congruent to 1 mod of phi of n. Can you do this calculation? You might have to do some trial and error. So I'll give you the value right now. Let's say if we consider the value 23 for D, okay, can you multiply it with the public key? What do you get? So when you do 23 dot, I'm sorry, not dot, multiply by 7, that is D into E, you have 1 mod 160. Okay, what does it mean? One sixty mod 161 mod 60.
1.
Right. So this congruence relationship, I am resolving it to the equation. So 161 mod 160 is 1, and both the sides give you the 1 result. So that's why this condition is satisfied. Okay, which condition? We have to I hope the screen was visible to you.
Yes, sir.
Actually, see, I have shared only this screen with you. Okay, just one screen, not the complete screen of my laptop. And when I was doing the calculations on the calculator, I was on this other screen. Can you please tell me during that time, were you able to see this calculation while I was writing on the screen?
No, sir.
It was frozen.
Yes, sir.
Okay, so when I move to other screen, it freezes. Okay, so I was talking about, let's consider the value 23 for a private key. Okay, and when we multiply it by the public key, we get this value 161, and it gives you, it satisfies this condition. Okay, the multiplication of D and E is congruent to 1 mod of phi of n. Phi of n is 160 here. Okay, so here what happens is D is 23 and E is 7. Okay, and always remember, a public key is a set of two numbers, D and N. I'm sorry, E and N. And private key is also a set of two numbers, which is D and N. Okay, so now we'll move to the calculation here. Okay, let us consider M is equal to 88. Okay, can you do the calculation with this one? How to produce a ciphertext? 88 raised to M raised to E. E is 7 here. Mod N. What is N? Anyone? N is 187. So last time we have seen how to calculate the modular of a large number. Can you solve this now? if you calculate these three values, 4 plus 2 plus 1, will it give you 7? So what is this 88 mod 187?
So it would be 88 only because
88, that is correct. This one? You may use the calculator for 88 raised to 2.
So it is 77.
so it's 77.
Okay, good. 77. And this one?
So we can write 88 raised to 4 as 88 square mod 187 and 88 square
Yeah,
mod
this
187.
can be, 88 raised to 2 raised to 2. This is possible. So 77 raised to 2, that is also possible.
So then 77 raised to 2 will be 154.
But again, you have to do mod 187 after that.
So then also it would be 154 only, right? Because
So it is 132, I think.
154 and 132.
no, so it was a calculation mistake. So it's 132 only.
132. Yeah. Shall we rest on 132? Rest of the. Everyone, please calculate this and will confirm. So 88 into 77 into 132 mod 187. And that will be ciphertext.
So it is 9.
9. Is there any
Yes,
other answer? What is this product? Calculate it.
so it is 894,432.
894,432 mod 187.
11, sir.
11.
Yes, sir.
Okay. Any other answer? 13.
Yes, sir, it would be 11. It was calculation mistake.
Okay. Shall we rest on 11 then?
Yes, sir.
Okay. So if you are sending actual original message as 88, okay, and if you apply the RSA algorithm, the ciphertext would be 11. Okay. Now, when you do the decryption part, okay, what you have to do with the private key, C raised to D mod N. Okay, what is C? 11, D is 23, mod N is 187. Let us calculate this. You can directly so either you can do 11 raised to 1 mod 187, 11 raised to 2, 11 raised to 4, 11 raised to 8, plus 4, 2, 12, 16, 16, 4. Yeah. So you have to use 11 raised to 8 twice, this into 11 raised to 4. That will be 20. This is 1, 22, and this is 1. That will 10, 23. Mod 187. If you're doing the calculation, if you got this, this will be 11. This will be 121.
It would be one.
Which answer you are giving me?
So the third part, it would be 222.
222.
No, sir, only 22.
Okay, only 22. Okay.
No, sir, sorry, sir, it's incorrect. I thought it is 11 to the power 3. It is 4 actually.
Right. Or you can do 121 raised to 2 mod 187 for getting this answer.
So it is 55.
Okay. Any other answer? Yeah, this is correct. 55 is correct. Or if you can do the direct operation on this calculator, that is also okay.
Next one is 33, sir.
33. Any other answer? So
So for the last one, why did we do the 55 to the power 4?
because 11 raised to 4 is 55. I'm sorry.
Yes, sir.
This has to be 55 raised to 2. I'm sorry. So for 11 raised to 8, what I'll do is no, not. I'm confused now.
It is 33. Answer is 33 for the last part.
Yeah, this is correct. Okay. So what is this? 11 raised to 4 raised to 2? Is it 11 raised to 8?
So it is. Yes, sir.
So that's why I have written 55 raised to 2, because 11 raised to 4 mod 187 is 55.
Yes, I am giving the answer after 55 raised to 2. The
Okay.
answer is 33.
Okay, 33. That is correct. Okay. So now you have to multiply all these numbers. 11, 55, 121. I'm sorry, the sequence is wrong. 33. No, again, is it correct? You have to take this twice, right? Because for 23, 8 plus 8, that is 16 plus 4, 20 plus 2, 22 plus 1. So this you have to do, I'm sorry, twice. 33, you have to take 2 times. Mod 187.
So its value is 79,720.
Hmm?
245.
245. Everyone should get these values correct.
The answer is 88.
Answer is 88, which is a original message. Okay. So this is how RSA works. You can take the example as P equal to 3 and Q equal to 11 and solve this example with RSA. This is a bit simpler example than this one, whatever we have seen. Okay, you can do this on your own. If you have any queries, do let me know. Give you the algorithm here and the public key, private key screen. You must have few doubts.
Sir, could you show the 11 raised to 23 solution again?
Okay, just hold on. Lost the sheet. Just a minute. Must have it somewhere. I'm sorry, I have not written
Sir,
all
sir.
the steps. Yeah.
Sir, in this, once we found out the modulo values, we just multiplied them, and in the end, we did a modulo again.
Yeah, because what we are doing here is we are using that arithmetic, modular arithmetic distance. If you remember, A mod n into B mod n of mod n. If you want to find out this, then it is equal to A into B mod n. So this is the property that we have used here. So what we want to find out is 11 raised to 23 mod 187, that we have written as 11 raised to 1 into 11 raised to 2 into 11 raised to 4 into 2 into 11 raised to 8. So this will be 16, this will be 4, that is 22. I'm sorry, 20, plus this will be 22, and this will be 1. So this is 23 division of 11 raised to 23. Okay, and the whole mod 187 we want to calculate, right? So what we have done is this mod 187 we have entered into each item, and then we have calculated 11 raised to mod 187, 11 raised to 2 mod 187, and so on. And at the end we have done the product. This is the product, and did the mod 187 again.
Yes, sir. Got it.
Okay. I'm sorry guys, let me stop the recording.